123 to 125. And just page 125, you need to read the top of this page. Okay, so this is the next homework, guys. So let's now, guys, move to the next chapter, and in this chapter we will study the periodic potential. I will try to define the periodic potential, but before that we need to go back to quantum mechanics. It's very important to do that. And if I go back to quantum mechanics, I will remind you this simple problem. So let's do that before we start talking about the periodic potential. Just, guys, to help you to remember this problem. So what we have right here, we have finite potential well. I will try to give you kind of sense what will happen to the electron wave function inside and outside. And then I'm going to review with you guys the step potential, and then we will go to the periodic potential. Because actually the periodic potential is a combination between the finite potential well and the step potential. It will repeat it more than one time. So it's a good idea, guys, to show you that. So here we have V0. So V0, guys, represents the potential for this potential well. So we can here consider that we have zero potential, and here we have V0. So the whole thing here represents V0. Also here we have V0. Inside the potential well, guys, we have zero potential. So there is no potential here. So we have zero. So we have zero potential. Okay, outside here we have V0. How can we deal with this kind of problem? Just let's try to understand that and go back and review this. How can we deal with this problem, guys? So what's the first thing that we need to think about? The first thing that we need to think about here, guys, is a Schrödinger equation. We need to use Schrödinger equation to deal with this kind of problem. Of course, we know in classical mechanics the total energy is equal to kinetic energy plus potential energy if we deal with mass. But in quantum mechanics we are dealing with waves instead of masses. To be precise, we are dealing with the superposition of waves. Okay? Now, guys, if we look at here, we will see that we have region number 1, and we have right here region number 2, and here I have region number 3. So we have 3 regions here, guys. And also, I would like to tell you that there is a width for this finite potential well. So maybe here we have maybe 0, and here we have A, and this represents x-axis. So this is 0, and this is A, that represents the width, and the height actually is the potential. Okay? So let's do that. This is finite potential well. Let's now try to write a Schrödinger equation for this problem. Before we do that, we need to look at these regions, guys. I will start with region number 1, which is I. So what I'm going to do here, I'm going to write Schrödinger equation. Schrödinger equation should be minus h bar squared over 2m, and I have here partial squared psi over partial x squared. I have the whole equation here just in 1 dimension, so we don't have it in 3 or 2 dimensions. And we need to add the potential that we have right here So we have here V0, and here we have psi, and that's equal to energy times psi. So this is the first equation. And for equation number 2, guys, so what do we have? We have minus h power squared over 2m. And also, I think it is a good idea to indicate psi as psi 1, psi 1, psi 1, because we are talking about equation number 1. So we have now partial squared psi 2 over partial x squared plus 0 potential. Plus 0 potential. So that means there is no potential. So this is equal to E times psi 2. And then write the third equation for equation number 3 right here, which is exactly like Schrödinger equation here. So it will give me here minus h power squared over 2m, and I have partial squared psi 3 over partial x squared, and here we have plus v0 psi, and that's equal to E times psi. This is psi 3, and this is psi 3. Now, guys, if we look at to this problem and try to think about these wave functions, psi 1 and psi 2 and psi 3. You still remember, guys, the infinite potential well problem that we did together. We did that in 3 dimensions, if you still remember. And we suggested that the solution is signed. So why is that? If we have the solution as signed, so that will give me high probability. So the probability actually, when we square the wave function, so that will give me the probability. So if we have the wave function as a sign, so that will give me high probability inside the infinite potential well that we studied. And if we go in this direction, the probability will go down. Actually here, guys, we have the same thing. We will deal with the sign. So the sign can be a very nice function for us, but there is something new that we need to add here. Yeah, so sign, yeah, sign something. Just we know that we are dealing with sign function. Why we use sign function here, guys? If we use sign function, so that will give me high probability. And if we draw, guys, the wave function should be like this. But if we draw the probability, always the probability is like this. Approximately like the Gaussian. Okay? So now I will show you the difference between finite potential well and infinite potential well. You will see, guys, if we have finite potential well, you will see that the probability is going outside like this. And also from the other side, the probability is going outside like this. So there is kind of probability here. What does that mean? That means we have psi 1 and we have psi 3. So this can represent psi 1 and this can represent, this can represent psi 3 and this can represent psi 1. So there is probability, guys, to find the electron right here. That's possible. There is a property, guys, called tunneling. And since this potential right here, guys, will continue to infinity, so we'll have the same potential if we go on this side. There is no difference. And if we go to that side, we will have the same potential. There's no difference. And that's why, guys, you will see that the wave function will go down, as you can see right here. And the wave function is going to go down, as you can see right here. So now, guys, if we try to write down these wave functions, we can do something like this. So I will try to do that. So sine 1 is equal to, and sine 2 is equal to, and sine 3 is equal to. Sometimes we don't need to solve the differential equations. Maybe we can see this behavior and that can help us to figure out the wave functions. Okay, so here guys we have negative values for x, and here we have positive values for x. We need to use function guys that decrease down if we increase x. It should be exponential function, correct? So if we have exponential, maybe I will use something here, so maybe I will use alpha x right here and use negative sign. So that's correct. So if I increase x, this function will go down, correct? If we have infinity, so we will achieve 0. Because this potential V will continue to be the same forever. And also from this side, it will be the same forever. Just here we have 0 potential. That's very nice. Let's consider number, oh, I'm sorry, this is 3. So this is 1. Okay, so let's do that. This is 3. We have minus maybe gamma x. So this is number 3, go down. So this is number 1, go up, as you can see. That's very nice. Now, if we look at this, this should have exponential plus alpha beta, beta x, and plus exponential minus beta x. We should have both of them, guys. And we will see if that works. Let's see. I think I need to add here I, and I will use, why is that, the complex number I? Because if I go to Euler equation, which is exponential I beta x, it is equal to cosine beta x plus I sine beta x. And exponential minus I beta x, that will give me here cosine beta x minus I sine beta x. Let's see if we have sine. If I add them together, let's see here, if I add them together, so that will give me, this will be cancelled with that. So that will give me here, so we'll have 2 cosine beta x. So that will give me cosine. Let's see. We should have sine here. Let's think carefully about that. So here we have 0. Okay, and here we have a. If we consider the 0 at the middle, okay, if we consider the 0 at the middle, so that will give me highest amplitude for the cosine, and if we go to this side, so the cosine will go down to 0, and if we go to this side, the cosine will go to 0. So maybe I can do that. Yeah, just to avoid overthinking about that. So we have minus a here, and we have positive a, and that's fine, guys. There is no problem. And here we have 0x. That's fine. If we have something like this, so cosine should work. That's totally fine. So highest amplitude, and then go down, and then go down. Okay, that's very nice. So now, guys, these solutions are very important when we study the periodic potential. So maybe here we can add normalization constant A. Here we can have B. have C, so A, B, C, and here we can have D. The A, B, C, D, these are normalization constants. Okay? So A and B and C and D are normalization constants. Okay, we can find them if we normalize the wave function. That's totally fine. But this is not our goal, guys. Our goal to understand this behavior. This behavior for probability. I will write that down. So here we have psi squared. This is the probability. Since we have finite potential well, there is small probability here to find the electron right here, and there is another small probability to find the electron here. That is very nice. Now guys, this is the first part of the periodic potential. Let's go now guys to the second part, which is the step potential. So, and don't worry, I will post this recording and you will have all of these equations with you. But let's think carefully about that. I will maybe come here and draw the step potential and see how can we deal with the step potential, guys, using quantum mechanics. So we will use the same idea, but there are very important things. Also, I forgot to indicate to something here. I will do that right now. It is very important. So this is the step potential, as you can see right here. It has potential V0. So here potential is equal to 0, here potential is equal to 0, and here the potential is equal to V0, because there is a height. Yeah, like this, so it is step, as you can see right here. Now, just would like to mention to this important thing is, when I solved this problem, I assumed that the energy of the electron is smaller than V0. So that means the electron has energy lower than V0 when I solve this problem like this. But there is another question, so maybe it's a good idea to share that with you guys. What will happen if the electron has higher energy than V0? Will the electron be affected? So let's assume that we have electron moving like this, as a wave, of course. So what will happen to that electron? So if the electron is a wave, so that means it has frequency and it has wavelength. So what will happen to those two? I can draw that here for you guys. So when the electron is going like this, I don't know if that's clear. We can use the blue one, guys, so you can see that color. So the electron, guys, has energy higher than V0 and going like this, so what will happen? So the electron is a wave. So it will move like this until the electron achieves this side. Once the electron achieves this side, so what will happen? You will see that the wavelength of that electron wave function will be shorter, as you can see right here. So that's strange. Look at. So the finite potential will affect the electron wave function even though the electron is moving up. Okay? And then return back to the normal behavior. So you will see here that you have here long lambda and you have small frequency. Here you have short lambda and you have like higher frequency, and here you have long lambda. So how do we link frequency to lambda, guys? You can use this equation. So the speed of the wave is equal to frequency times lambda. So frequency is equal to c over lambda. If this is long, this is small. If this is short, this is high. But this is what will happen, guys. I prefer to share that with you, because that can happen if the electron is moving just like over like periodic potential, and that can be repeated, okay? And if the electron is inside, it will be dictated by this behavior, guys. Outside, it will be dictated by that behavior. So the finite potential will is strong, guys, and can do changes to the electron wave function. Now, guys, let's come here. And what I will do here, guys, I will assume that I created here kind of potential step here. Let's do that. This is a potential step. Of course, this is going to change. I will show you that right there. So it's not going to go to zero anymore, because this became with a smaller width. It never got to infinity. So we have just a step here. So let's see what will happen now to the electron, guys. So we have region number 1, and region number 2, and region number 3, as we did before. Here, guys. So we have region 1, and we have region 2, and we have region 3. And we can have here, for example, this is the 0x if you would like, according to what we have right there. Yeah, so this can be maybe positive A, maybe this is positive 2A. That's fine. Okay, now, what will happen to the electron, guys? If we have electron going from here, I will start from this point right here. If the electron is going toward this potential step, so what will happen? The electron will experience this kind of behavior. And that depends actually on the width of this potential step. So this is the electron going like this. And of course the electron has energy smaller than V0. The electron is down right here. So the electron will go in this direction, as you can see, and then actually what will happen, according to the tunneling idea, so the electron will go inside this potential step as a wave, of course. So the probability of having the electron inside will go down, until the electron go out from the other side. So you can see that there is probability to have the electron here, and there is also probability to have the electron here, and also there is probability to have the electron right here. So this is what will happen. And also we can use Schrodinger equations, guys. Sorry, we can use Schrodinger equation for those three regions to figure out the wave function of the electron here, and here, and here. So maybe I will write these equations for you. Let's see what will happen here. So these equations can be as the following. I will consider this. So here we don't have any potential. So potential here is 0. So it should be this equation right here. So I will do minus h bar squared over 2n, and we have partial squared psi over partial x squared, and that's equal to e times psi. This is psi 1, and this is psi 1. Inside, we need to consider the potential and include it in Schrodinger equation. So we will have minus h bar squared over 2n, and partial squared psi 2, partial x squared, and here plus b0 psi, and that's equal to e psi 2, 2, 2. And for region number 3, of course, we have this equation again, so we'll have minus h bar squared over 2m, partial squared psi over partial x squared, and that's equal to e times psi. This is 3, and this is 3. Now, let's avoid solving these differential equations. Actually, you can solve these differential equations, that's fine. You can move this to the left-hand side and make this equation equal to 0, and divide the whole equation by h power squared, and multiply the whole equation by minus 2m, so that will give you something like this. But we are not going to do that. Let's focus on the behavior of the electron that can help us to figure out the wave function. You can do something like this. So, minus 2me over h bar squared psi, and that's equal to 0. Maybe you call this maybe alpha squared, and solve this differential equation. It's not hard to solve this equation. But we are not going to use this idea. We are going to use the behavior of the electron. Since the electron, guys, is wave, like electromagnetic waves. So when the electron hits this side, or this barrier, so what will happen? Some of the intensity of that wave can go through, and some of the intensity can be reflected. So we can see something like this. This is incident wave, and this is reflected wave, and some of the wave can go through. And also this wave, guys, when this wave goes through, we know that the amplitude of this wave will be reduced, and the probability to have the electron will be reduced when the electron go like this. But since we have this barrier with certain or specific width, there is a possibility for the electron to go out. So that means we will have again reflected wave and another wave that can go outside. So incident, reflected, incident, reflected, and then just go out in one direction. So this is what will happen. Now let's try to write these equations down and use the idea of the exponential. So we have psi 1, I have psi 2, and I have psi 3, that's equal to, that's equal to, and that's equal to. So psi 1 has incident and reflected. And we need to maintain here the idea of cosine or sine. We need to maintain that idea here. So that means we can have exponential, we have here positive, maybe alpha x, plus exponential minus alpha x. And right here, we need, guys, we don't need to maintain here the idea of sine or cosine, but we need to respect that there is, sorry, here we need to have I alpha x, and here we need to have minus I alpha x. So here we don't need to maintain the idea of sine and cosine, but what we need to do here, guys, we need to respect the incident and the reflected. Okay, so if we do that, we don't need to use the I here. We can do exponential plus beta x plus exponential minus beta x. Okay, so that works. And for this one, guys, we can see that the probability can go up again. So the electron will go out, go down, and then go up again when the electron go out. So we can have here exponential, and we can have here plus I gamma x. And we can have some constants here, A and B and C and D, A, B, C, D, E. these are the normalization constants. Okay, and I will double check. Maybe I wrote something wrong here. Just to double check. Yeah, that's right. That's correct. So these equations are correct. Yes. This is for region number 1, this is for region number 2, and this is for region number 3. And this is what would happen if the electron has energy lower than the potential right here. What will happen if the electron has energy higher than the potential? So you can apply the same idea, guys. So this step is going to affect the wave function of the electron. Okay, even though the electron has energy higher than this step. So that is really nice. We can see something interesting, guys. Let's try now to repeat this kind of problems, like more than one time. So we have here zero potential, we have V0, zero potential, V0, zero potential, V0. And see what will happen. If we do that, I will erase this part. If I do that, guys, and repeat this step potential more than one time, and this finite potential more than one time. So we'll have something like this. Maybe I will have maybe 2 copies or 3 copies, and that's enough. Let's do that. Do that. And we will have another one and another one here. That is very nice. So let's try now to close this from here, and 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 close this from here. That's very nice, guys. This is going to continue on this side, and this is also going to continue on that side. So we have this repeated like more than one time. We have the same index. Okay? Maybe we can have the 0 here just to link everything to this. So we have 0, minus A, minus 2A, and here we have plus A, and here we have plus 2A, and here we have plus 3A, and maybe here we have plus 4A. Okay. Oh, let's see. So A and A, that means we have 2A here. Oh, we should maintain 2A even here. So we have 2A, we should have here 4A. So we should have here 5A. So you can see now the weight here is A. I have the same weight here as well. So it is A, and here the weight is A. And the weight here is 2A, and the weight right here is 2A. And all of these steps have the same potential, which is V0. Okay? Now guys, this kind of potential is called periodic potential. Actually, you have the same scenario, you have the same idea. So step finite potential, step finite potential, step finite potential, and etc. You can have 100 or 200 of these potentials. But what I would like to mention here, this kind of potential has a name. They don't include the name. So there was a guy started with this idea before Bloch. I forget his name. I believe his name is Kongor. I'm not sure about that, but I will bring that name. So there is a guy started with this idea, which is periodic potential like this, with finite potential followed by step potential, finite potential followed by step potential, and etc. And he did study for this kind of periodic potential. And then after that, there was a guy, his name Bloch, came and started working on this idea. And he linked this idea to the crystal structure that we have. So what Bloch said, he said the following guys. He said, if we have like array or line of atoms, for example, if we have array or line of atoms, as you can see right here, maybe we have one atom here, and we have another atom right here, and another atom right here, and another atom right here. Okay? Maybe this represents x-axis just to know the position of these atoms. So we have 1, 2, 3, 4, but it is possible to have infinite number of these atoms going on this side and going on that side. Okay, this is just in one dimension. Now, if we try to draw the potential, this is u as a function of x. Now guys, what Bloch mentioned here, he mentioned that those atoms have kind of field around them. This field, guys, that can be created by these atoms can create periodic potential, as you can see right here. If I consider just one atom and try to draw this potential, you will see that the potential is going down here and going up here. Okay, so let's go up from this side and go up from this side. But it goes down here. If I create more than one atom here, I will notice that I have this kind of potential, guys. Yeah, something like this. Maybe there's another atom here. It should have the same height. Right here. And maybe here we have the 0. This is atom 1, atom 2, atom 3, and atom 4. So this is what he assumed. And also, guys, you can see that, let's see here, that's correct, yes. Let's see here. Oh, I made a mistake. Let's draw that on the opposite side of this. Let's draw that down. So we see what will happen. So, okay. So we have the potential like this. So sorry for that. So it should be like this, guys. It should be like this. And go like this from the other side, and go like this from this side, and go like this, and go like this. Okay, and this is the height. This is the height of the potential, guys. Yep, right here. So now, guys, you can see that we have, not exactly, but we have something similar to that. We have something similar to the finite potential will and stiff, finite potential will and stiff, finite potential will and stiff. And if the electron, for example, try to go outside of the atom, if the electron, for example, try to go outside of the atom, so what will happen here, guys? You will see that there is a potential will here. Okay, kind of potential. So this can go approximately to infinity. Yeah, because that can keep the electron inside. The electron can't go here and can't go here. Just keep the electron here inside. And if the electron decided to jump over this potential, that means the electron needs very, very high energy. That's higher than the potential energy that we have right here. Just maybe to jump to the other atom. Okay, but you can see that this potential can be repeated more than one time. So what Bloch did here, guys? He also used Schrödinger equation and considered of course the potential as a function of r, and what he did here, he did minus h power squared over 2m, just solved Schrödinger equation. Del squared, this is in 3 dimensions, and I will tell you what's del squared here. Here we should have psi, and here we have plus. U as a function in 3 dimensions should be function of r, and here we have psi again, and that's equal to the energy times psi. So this is actually represent the potential here, guys. And then you solve this equation, and when you solve this equation, guys, notice that the potential actually is periodic. What does that mean? So let's assume that here we have r, and right here maybe we have r plus a. Maybe right here we have r plus 2a, and here we have r plus 3a. So you notice that the potential u of r actually is equal to u as a function of r plus a. And it is equal to u as a function of r plus 2a, and etc. So it is periodic potential. Even though you are changing r, but you have the same potential. So this is what he created here. And next time we will go through deriving the wave equation for Bloch wave equation. It is a very interesting equation. We will go through that. And I believe this introduction can be very nice to help you to understand what will happen if we have periodic potential. Now let's see what is the importance of this periodic potential. Actually we have crystals, and these crystals have an array of atoms, as you can see right here. You still remember, guys, when we draw the cubic structure, so we do something like this, and we have some atoms here, but actually there is no bonds here. Actually, even in chemistry, the bond doesn't mean that there is like stick between the 2 atoms, so that's wrong. The bonds bond means that there is kind of potential field between those 2 atoms that can keep this atom at this position and this atom at this position. If we, for example, increase the temperature for this unit cell, for example, increase the temperature for this unit cell, so what will happen? You can see that those atoms can vibrate. That's possible. And you will study, guys, that when you continue doing graduate study. So you will study what will happen if we have vibration, and that's included here in this book. Okay, there is possibility for the atom to vibrate. That's possible. Some people deal with this kind of problem as springs between those atoms, like this. And this represents the force field, for example. Yeah, they use Kx. They use Kx as a force field. But this is a toy model, just to help you to understand what will happen. So there are vibrations that can happen, but in reality, what prevents those atoms from maybe going further, go away from this position? The thing that can prevent those electrons from going away, this field right here. So this field can maintain the position of these atoms. So atoms can't move away, and at the same time that can control the movement of the electron. Okay, so the electron can be trapped here inside. It needs high energy to jump over this potential. Okay, so I think we are done for today, guys. I don't know if you have any questions, any concerns, so we can talk about that. Yeah, so yeah, otherwise, if you don't have any questions, so feel free to go. And just to remind you guys, so the final exam will cover just 2 chapters, which is 3 chapters, I'm sorry, 3 chapters, which is chapter 6, chapter 7, sorry, and chapter 8, and chapter 9. And we are not going to study the whole chapter 8. We will study some of chapter 8. Okay? And also I'm thinking to make the final exam as take-home exam. I don't know if you like this idea. Yes. Absolutely, sure, I will do that. Yeah. I will post your homework as well. So feel free, please, if you don't understand anything, to email me about this topic, of course, and I will be happy to answer you guys. Yep. Thank you so much.